In order for a skeletal muscle contraction to occur, muscle fibers have to be excited by the motor neuron that innervates it. This process of excitation can be explained by events at and leading up to the neuromuscular junction. The chemical synapse is formed between the motor neuron and the end plate of the muscle fiber. In the case of the neuromuscular junction, our main transmitter is going to be acetylcholine. And in order to cause a muscle contraction, a flood of acetylcholine must be released into the neuromuscular junction to bring about a large end plate current of the neurotransmitter. This current is essentially the wave of many ion channels due to the opening of acetylcholine vesicles and binding. It has to be fast in order to generate a quick muscle contraction. The flood is necessary to generate a large end plate current, which leads to a large change in the end plate potential. Without a flood of acetylcholine, only miniature currents are generated. And with acetylcholine esterase, a superfast enzyme that's job is to degrade acetylcholine in the synaptic cleft, acetylcholine will degrade before it can do its job. You can kind of think of acetylcholine esterase as a Pac-Man eating up all the acetylcholines. Alright, so next I'm going to draw a membrane with a pretty negative, let's say negative 70 millivolts end plate potential. So at this point, since acetylcholine has binded to the channels and has allowed them to open, a sodium channel would allow sodium to flow into the cell in pretty large quantities to begin to depolarize the membrane. But in the neuromuscular junction, around 0 millivolts, you find the reversal potential, where sodium has no particular desire to be into or out of the cell, so you have no net flow of the ion. Next, let's say you super depolarize the cell, something crazy, like positive 100 millivolts. Sodium is going to want to leave the cell. It has no desire to be in there. The dude wants to get out of the party. The house is on fire. Similar to sodium, other ions will behave differently at other membrane potentials as well, where each ion will have its own reversal potential based on its electrochemical gradient. Alright, next we're going to kind of talk about end plate currents a little bit, because that's after the acetylcholine was released into the synaptic cleft. That's what started this whole thing. So the end plate current can be calculated as the product of the driving force and the ion conductance. So when either of those is 0, there is no end plate current, and there'd be no driving force in the reversal potential, and there'd be no ion conductance in some other situations. And because of just basic algebra, you've got the larger the conductance and the larger the driving force, the larger the end plate current is going to be. And we get the driving force from the Nernst equation we talked about a couple chapters ago.